Little Dipper Elementary, an interactive climate exploratorium. Hi, I'm Danielle Valdez. Working on this project has been an incredible experience. Our team successfully created an environment where we could be highly collaborative and experimental.
Hello, I'm Catherine Marple. I have enjoyed designing from a child's perspective, where everything has potential for creativity and interaction.
Hi, I'm Garrett Lever. I loved exploring the relationship between play and technical systems.
Hey, I'm David Dyson. I am humbled to have had the opportunity to work with such great people on an amazing project. And finally, this project would not have been possible without our professor and mentor Ihab El-Ziyadi.
This presentation is split into 7 parts: the origin of our journey, site constraints and opportunities, big questions, goals and guidelines, the Solar Decathlon contest, reflections, and lastly, a conclusion.
Our Solar Decathlon journey started in January as a 10-week architecture studio led by Professor Ihab El-Ziyadi. The studio challenged us to design an energy-efficient school between the United States and Mexico. Individually, we explored metaphors of insertion, threshold, reciprocity, materiality, and infrastructure. These experimental models helped us to start thinking about what a net zero elementary school just 1,500 feet from the United States and Mexico border might be. This school inspires students to learn big concepts by breaking them into kid-sized learning moments through interactive objects.
Constraints and opportunities. Between Mexico and the United States, a hard line stretches over 1,900 miles, dividing countries, cities, ecologies, and even families. Our site is located in Tecate, California, 1,500 feet from this border. Sheltered by mountains at 1,700 feet elevation, Tecate experiences a climate close to that of San Diego, California, with much of the year being within the comfort zone. 2 incredibly different demographic and spatial environments exist, separated by a thin border. Tecate, Mexico is a dense suburban city and a destination for tourists. Tecate, California is an international trade community and gateway between the 2 countries. While there exists a physical wall between the 2 cities, they are far from independent of each other.
With a population of 73,000, the density of Tecate, Mexico in relation to the 650 people of Tecate, California leads to a flux of diverse interaction across the border. Tecate, Mexico is demographically diverse and culturally rich, while scattered residents, government staff, and industrial workers reside in Tecate, California. Due to this imbalance, the school has potential to bring the 2 communities together, as a majority of students come daily over the borders from Mexico.
Climate change, border injustice, overconsumption. We asked ourselves, how can we teach children about these global challenges? And how can design teach children about these global challenges? In order to explore these questions, we look to how scientists and researchers study problems. A common tool for them is the neutral field, such as a petri dish, a glass slide, a vacuum. They allow phenomena to be isolated and studied individually. This led us to ask the question, what if we break down global challenges into kid-sized learning moments that could be highlighted against a neutral field?
The seemingly incomprehensible issues humanity faces, such as climate change, must be taught to children as they become the next stewards of the environment. These complex challenges are symbolized and broken down into kid-sized, interactive exercises through the school's design. As architecture and form take a back seat, climate systems and interactive objects become drivers of the student's education at all scales.
Students are given responsibility over their classroom. Under the teacher's guidance, students operate active and passive climate systems, rearrange the spatial organization, and learn how to be responsible stewards of their environment. The classroom cluster is a hub for students and teachers. It acts as a safe place for fostering relationships, learning, and exchanging cultural values. The site is organized on a 5-foot grid that represents the neutral field. The classrooms and pavilion structures are aligned to this grid and become parts of the neutral field. The two community buildings break the grid and stand out on the field as specimens. This relationship to specimen to field, community to school, fosters student connection to each other, staff, and the local community.
Throughout this project, a conceptual kit of parts organizes the presentation and explains our design thinking. This kit of parts consists of two critical concepts: specimens on a field and interactive relationships. Different objects and systems correspond to specific learning guidelines: reciprocal energy, kids as stewards, inhabitable threshold, emergent play, and beauty is for everyone. Throughout the presentation and in the architecture itself, these guidelines are indicated with their corresponding color, visually telling the story of interactive learning moments and energy strategies. Next, we will dive into our response to the decathlon competitions.
As Newton's third law states, for every action there is an equal and opposite reaction. This energy balance is physically represented throughout the project in the objects, systems, and architecture. Little Dipper Elementary is a net positive school. We use 3 main strategies to achieve this and reduce energy use.
First, minimize conditioned space. By providing covered outdoor circulation and gathering spaces, we reduce conditioned volume. Outdoor circulation is common for schools in this climate, minimizing demand for mechanical systems. Second, utilize passive climate systems. Solar chimneys, low windward vents, and cooling ponds allow for natural ventilation and evaporative cooling, while thick walls on the east and west reduce heat gain and increase thermal lag. And optimal use of daylighting reduces the need for electrical lighting. Lastly, simplify construction, material use, and operations. Tied to our marketability strategies, we designed with accessible, understandable, and affordable systems in mind.
We ran analyses in Integrated Environmental Solutions Virtual Environment, or IESVE. Using baseline climate systems, our model resulted in net zero energy use intensity, or EUI. With our proposed passive climate systems, we exceed the target site EUI of 19 with the projected site EUI of 13. With on-site generation, the school achieves a net EUI of -10. Little Dipper Elementary produces more electricity than it uses with a standard monocrystalline photovoltaic array. While most energy is used on-site, leftover energy can be supplied to the local power grid. Energy systems are not only typical, but novel as well. Still under development, high-altitude autonomous kites can be tethered to generators on rooftops to produce energy. The prominent visibility of the kite also acts as a beacon that can be seen across the border, reassuring families through a visual connection to their children.
Engineered systems on display show students the reality of how buildings provide shelter. Accessibility and simplicity drive the design of the structural systems, allowing the school to put more money into vibrant learning experiences. The classroom consists of prefabricated wood-framed wall panels with an exterior CMU layer. Laminated wood beams span the distance between the walls and support the flat roof. Continuing the tradition of industrial construction in the area, the community buildings are made of widely available prefab steel trusses, with knowledgeable builders and materials close by. Prefabricated modular pavilions are assembled on-site with standardized structural square frames that can be fitted with a variety of infill panels.
Radiant floor slabs make the classroom cozy by the time students arrive. In cooling mode, passive chilled beams cool rising hot air. Low windward intake vents sit above an evaporative cooling pond, cooling supply air. Roof monitors provide evenly distributed and adjustable daylight for classroom activities. Classroom air is kept fresh via an energy recovery ventilator. Inoperable roof monitor windows work in tandem with low windward facing vents. In the community buildings, we wanted to reflect the industrial vernacular and utilize a standard high-efficiency HVAC system.
The community building's wall assembly, which wraps the roof, can be summarized as a highly insulated industrial warehouse. Following passive house principles combined with prefab wall assemblies, the classroom wall is designed to maximize thermal insulation and affordability.
Little Dipper Elementary reduces its water use by implementing a cradle-to-cradle approach to waste. Composting toilets and compost gardens teach students about taking responsibility for their own waste, and rainwater collection reduces dependence on city water.
We believe that beauty is for everyone. This value is carried throughout the project to create equitable access to beautiful spaces by reducing maintenance, operations, and construction costs at every scale. We designed buildings that were inspired by the local vernacular. This means that maintenance and repairs can be contracted locally, and the low-cost, durable industrial materials can be sourced locally as well. A variety of factors reduce maintenance needs, reduce energy consumption, and reduce operations costs. Passive, along with low-tech systems, means fewer moving parts likely to break. The exclusive use of native vegetation fits seamlessly into the site's ecology, requiring less human intervention. And most importantly, student participation in daily maintenance and operations is integrated into the curriculum, inspiring students to become responsible stewards of their environment. We estimate that construction costs will be between $3 and $5 million. At around $150 per square foot, this energy-efficient and innovative school can be built for equal to or less than the average cost of an elementary school in the United States. Our biggest savings come from low-tech systems and student participation in daily maintenance and operations. But each user group has a part to play in reinforcing the message of stewardship and creating an environment where students can easily maintain and operate their learning spaces.
Tecate, California exists on a dynamic site, experiencing seasonal wildfires, periodic power outages, and a fluctuating economic and political situation requires any proposal to prepare for changing circumstances. In the scenario of a wildfire, the community clusters serve as a shelter for the surrounding community. The highly insulated assemblies provide higher fire resistance than typical industrial or commercial buildings, and the large open floor plan provides ample gathering space. The community cluster solar panels generate more energy than needed for building functions. The diagram shows the flow of excess solar energy generated by the gym building. The panels outlined in yellow send their unused energy to an on-site battery to be used in the event of a power outage. Site security proved to be a less than straightforward solution for this project. We discovered that a typical security measures go against the goal of creating inhabitable thresholds. Our solution was to adopt a scatter and run methodology for the general site combined with smaller lockdown zones as indicated in gray. While we would like to believe this project contributes nothing to global warming, such is just not the case. Low emission choices had to be balanced with resilience and cost, resulting in consumption of materials being the greatest source of greenhouse gas emissions in our project.
Inhabitable thresholds suggest that barriers do not have to separate, but can be utilized for the benefit of inhabitants. Visual connectivity between spaces, lack of corridors, open gathering spaces, and modular yellow pavilions stem from this concept. Central community zones are connected to private learning zones via outdoor learning and play areas. The community clusters and playfields are intended to be used as recreation places for both students and community. Different levels of enclosure provide shelter and security, from fully enclosed buildings to semi-enclosed pavilions to covered circulation to open fields. This spectrum of enclosure breaks down thresholds and increases energy efficiency. A grid overlaying the site designates ground conditions. Squares of concrete fill a central puddle shape connecting clusters. Local plantings at different densities fill grid squares and act as specimens on the field.
The community cluster serves as a prominent face and entry of the site. As students, faculty, and community members enter, the central core welcomes them, and the lobby provides a place to wait. Going north, they pass through the library, with a craft center at one end and the staff lounge at the other. Going south, they pass through a set of doors, isolating the quieter functions from the boisterous areas of the gym, kitchen, and music room, before making their way to the classroom cluster. Entering the library, students and staff interact with scattered blue bookshelves. Pink reading rooms dance under HVAC ducting and fabric clouds, diffusing daylight. In the craft center, students paint and play. The climbable pink mound provides a great place to read. In the gym, yellow sliding panels are pushed open and students prepare the elevated music room for a performance.
4 classrooms create micro-communities of students and staff. Students of similar grades share a panelized pinup wall and exchange ideas. Students garden together and roll back the courtyard shading device in good weather. A central courtyard is both the main entry to the cluster and a gathering place. A mound with a unique identifier acts as a landmark, giving each cluster an identity. Here, learning moments take the form of interactive and functional objects. You can see students playing ball near the mound, the shading device diffusing the bright sun, and the climbable objects of the playground framed beyond.
Orthogonal and accessible, the classroom is designed to be neutral, to provide a blank canvas for interactive learning. Interactive relationships include movable storage shelves, desks, and adjustable passive systems. Students push vibrant movable storage shelves back and forth to make both large gathering or small breakout zones. Their desks combine chair, table, and storage, fitting together for easy organization and flexibility. Students learn about the effects of daylight through manually adjusting fabric clouds that hang from roof monitors. Each element is intentionally designed to engage the students.
Students also engage in the school's operations on a deep level. Through playful switches, students cycle through climate modes in the classroom with indicators letting them know what the wind is doing, what temperature it is outside, and how much solar radiation is available. Temperature and humidity sensors placed in the classroom and the community buildings collect data, doubling as a climate curator.
Little Dipper Elementary serves as a prototype for affordable net zero primary schools by combining prefabricated, site-specific, and customizable elements. Prefabricated elements are displayed in a catalog where clients are able to select from standardized classroom components. Add-ons such as pavilions can be added to classrooms or used as standalone structures. These systems allow for easy phasing of projects or future expansion. Site-specific elements respond to the context of Tecate. Components and structures respond to the local climate and vernacular while sourcing materials and contractors within the community. This map shows a few of the manufacturers, suppliers, designers, and contractors within just 5 miles of the site. Local community engagement during construction lays the groundwork for future relationships and has the potential to activate the school as public space during off hours.
Engineered systems on display teach students the reality of how buildings provide shelter. Students are given the opportunity to experience a net zero building and understand what that means. Students can concentrate on their tasks with comfort as 100% of the work plane area is above daylight factor threshold when utilizing just the roof monitors. The community cluster also provides ample light with skylights and windows. A shaded circulation axis provides connection through the site.
To encourage inquisition and practical experimentation, students are responsible for the acoustic environment of the larger community spaces. Both the gym and the library spaces have large acoustic clouds made of absorptive fabric. These clouds can be raised, lowered, or compressed to absorb more or less noise. A switch allows students to control their acoustic environment through preset modes. Indoor air quality is kept fresh through low-emitting materials, optimal active ventilation systems, and night flush purging.
The heart of this project resides within the desire to create fun, interactive moments for children to be inspired to learn about and engage with the environment around them. A goal of holistic and responsible design was sought after. Similar to the Living Building Challenge, our project's goals address categories of materials, water, health and happiness, place, energy, beauty, and equity. We wanted to showcase that even the most common materials and methods can be used to make beautiful places. With a catalog of prefabricated building elements, schools can be designed quickly and affordably while still allowing for contextual interventions and high standards of quality. Like samples on a petri dish, students learn about passive climate systems, culture, and play through vibrant objects on a neutral field. These objects become tactile learning moments that simplify complex environmental systems. With objects like the interactive cloud, students learn about the direct connection between comfort and systems.
Finally, but perhaps most encompassing, is the goal for students to take an active role in adjusting their environment by interacting with educational elements. Whether for play, learning, or climate responsibility, students engage with these various elements to foster a sense of ownership for their own space through collaboration and exploration.
We understand architecture as a comprehensive subject that is a collaborative effort of multiple industries. Through this project, we have all gained a new admiration for our adjacent fields and their experts. We have also developed a deeper understanding of the incredible difficult social, political, and environmental challenges that exist on the border between Mexico and the United States. Through breaking down global challenges into kid-sized learning moments, encouraging active learning through interactive relationships, and letting the building be a stage for education, we believe that Little Dipper Elementary is a step forward in the exploration of these issues and represents an optimistic narrative for bridging the barriers and engaging with future generations.
Most importantly, this project asks not simply how a building can produce as much or more energy than it uses, but how a design, in every regard, can inspire children to be responsible stewards of their environment, ecosystem, and community. Lastly, we would like to thank all those who took this journey with us these past few months. Our professor, Ihab El-Zayadi, for his constant support and expertise, the students in our studio for sharing our excitement and laughing at our shenanigans, the caring reviewers for their thoughtful perspectives, and of course, the Solar Decathlon organization for providing us with a worthy challenge. Thank you for your attention and consideration.
Let's change the world together.